The map of how every neuron connects in my brain is unique. The map of how every neuron connects to every other neuron in your brain is unique. And even crazier, we think that if you had that map and you could read that map, literally we would know everything about you. And I realized maybe at that moment that what if many of these disorders, like schizophrenia, et cetera, are just sort of Peter Pan syndromes? As a scientist, I am not interested in trying to prove or disprove hypotheses. I am interested in finding that surprise that will overturn the existing worldview and replace it with a paradigm shift.
Welcome to Apple Finch Pudding, your gateway into the world of science. Today's scientist is Bobby Kasthuri, a professor of neurobiology at the University of Chicago. His work focuses on neuroanatomy and the connectome. Welcome, Bobby. How are you?
Good morning. Thank you very much for having me.
I'm happy that you're here. So before we start, my first question is always more or less the same. Do you have a fun science fact for our listeners?
A fun science fact. I'm hoping this entire conversation is a fun science fact. But I guess I have many science facts. Let's see if they're fun.
That's already a great start. I mean,
hey, I find them depressing, but sometimes people might find them fun. I think what we'll talk about today, which is my fun fact for the day, is that despite the fact that we walk around with these remarkable organs in our skulls called brains, and despite the fact that brains are responsible for almost everything you see in the world around you, human brains, we don't really know what makes human brains fundamentally special relative to all other animals. And given how different human brains are from other animals, I think that's kind of a crazy fact.
we really have no clue, or we have some ideas.
Fair enough. Of course, we're scientists, so we always have ideas, even sometimes before we have clues. And so, and so, for sure, there are lots of ideas for why human brains are special. I guess the most obvious one is that they're huge. A human brain is much larger than a mouse brain, for example. And it's not surprising, perhaps, given the size, that human brains make poetry and mouse brains don't, for example. So you could say, well, what do you care, Bobby? It's so obvious. There's a million times more brain in a human brain, so therefore that explains everything. And it raises a question of, okay, if I made a mouse with twice as big a brain, 5 times as big a brain, 10 times as big as a brain, is that mouse ultimately become as smart as a human? And fundamentally, is that all it takes? It's just a question of numbers. There are other theories that suggest perhaps that humans have special brain cells, neurons, that aren't found in other animals, et cetera. But I'll tell you, for a long time, at least looking under the microscope, not looking at the whole thing, but looking at actually what neurons look like, it is very hard for me to tell the difference, one versus the other. I happen to have my own idea for why human brains, again, with very little clues, just like the rest of the scientists. But yes, I think there are lots of ideas, but unfortunately, and I guess we could segue, there isn't really enough data.
Well, actually, before we delve further into that, so you're a neuroscientist, but could you explain to the audience what is neuroscience? What does a neuroscientist do?
Yes, thank you. So there's a broad field called neuroscience, which is really trying to understand how the specific organ in our skull, how brains work. And of course, it is a huge field because it's possible to study brains at many different levels. Some neuroscientists study the individual proteins and channels that are found on neurons that help them, do their functions. At the very other end of the spectrum, you could argue that economics is a field of neuroscience because it studies the decisions that groups of brains make together. You could make the argument that politics is a field of neuroscience. It's a fundamental question about how human brains make decisions. So among this huge spectrum, from psychology all the way down to atomic level, all of these are sort of dedicated to one idea with some ramifications. How does the brain work? How does it take in sensory information and make memories of it? How does it make decisions based on that sensory information? And for a large fraction of neuroscience, what happens when things go wrong? Probably most of your listeners know there are devastating diseases of the brain, ranging at the one end of age to Parkinson's and Alzheimer's, which are mental illnesses of the elderly, to the other end, autism spectrum disorders and other disorders, which are disorders of children. So a large fraction of neuroscience is figure out how brains work, and the other part is figure out what happens when they go wrong.
In this large field of neuroscience, where are you positioned? What do you do?
Great question. So I am of the view, again, just my view, that the best way to understand how brains behave is to understand how the individual cells within a brain behaves. One of my mentors told me this once, and it's stuck with me. You can imagine that all the neurons in your brain, for example, they have no idea that they're in a brain. They have no idea that they're processing visual information, or that they're storing a memory, or many of the things that they actually do. They're basically just cells in the weirdest pond in the world. But by that, I mean, there are individual cells in all of our lakes and ponds, these single-celled organisms, paramecium, et cetera. They operate by some rules, those paramecium. They want to live, they want to reproduce, et cetera. And to me, the brain is just a billion paramecium or 100 trillion paramecium in a pond with very little water. Most of the water has just been replaced with other cells. And so my argument is, if we want to understand how brains work, we should understand the behavior of individual cells of the brain. And then by taking those lessons and taking them out to collective, how all neurons work, is how we'll ultimately understand a brain. One version of this, just to go back to something we said earlier, you could study the field of economics, for example, where you study how tens of thousands of people make decisions. That could be potentially a complicated thing. If you understood the psychology of a single person and how a single person would react to this particular economic stimulus or this particular economic hardship, you could take that lesson and aggregate it, amplify it over 10,000 or 100,000 and make predictions how thousands of people would behave together. That's sort of where I sit. I think if you could fully understand, this is going to sound crazy, the psychology of an individual neuron, you could take that psychology, the behavior, and amplify it and understand how brains work.
And for that goal, you solely focus on neurons or also on other brain cells like glia and stuff?
Absolutely. So I think there are many kinds of cells that live in the pond of the brain. I think they're all valuable, but time is short, or life is short, I should say. And we have chosen a particular behavior about neurons, which the glia and the blood vessels all help with, just as a starting point.
So you study how those single cells function and then also how they work together. This sort of less brings us to the connectome. So could you explain what the connectome is and why it's so important?
Absolutely. So one way to maybe bring up the subject of a connectome is to ask, what is so special about a brain cell that's different than any other cell in my body? I have skin cells, I have stomach cells, liver cells, et cetera, et cetera, et cetera. And broadly, there are a few things that neurons have that other cells don't have. The first obvious thing by looking at them is most 99%, I should say, I'm going to say things like all other cells in the body, and then someone is going to find the one cell in the body that, so when I use words like all, I think I mean 95, 99, just to counter the future people.
Especially if scientists are listening, they're going to say, no, not 100%.
Exactly. And as one of them, I appreciate their criticism. So I think the first thing is when you look at them, almost every other cell in your body is fairly simple in shape and fairly symmetrical in shape. They all look like spheres or cuboids or to some first approximation. Neurons, however, look completely different. They have these elaborate processes that stick out of them. If you just look up a picture of a neuron, and in fact, we know that there are at least two kinds of processes. They have this huge tree that grows out of them. It looks very much like trees, actually, and it's often called the dendritic tree. And on the other end of them, they have a long cable that extends out of them, which is called an axon. And the reason neurons have these specialized features is they do something that no other cell in the body really does, which is to send their processes sometimes to the other side of the brain and make physical connections with those neurons. And in fact, the strong hypothesis in neuroscience is that the map of how every neuron connects in my brain is unique. The map of how every neuron connects to every other neuron in your brain is unique. And even crazier, we think that if you had that map and you could read that map, literally, we would know everything about you. We would know, since every memory is stored potentially in that map, every skill, every hope, every dream is stored in that map. The big idea of connectomics is if I can make a map of how every neuron connects to every other neuron in a brain, and you should push back, and I could read that map. We don't really know what that means just yet. But if I could read that map, that should really be you. That is the instantiation of you.
Before pushing back, I'm going to start with something else. So you have all those connections and they store your memories. So they store everything. So those connections change over time. Why do they change, or how do they change?
This is a great question. And again, I can only imagine how the scientists are going to react to this. I am of the belief that they don't change very much. And we have done some studies ourselves looking at how often synapses rearrange and remodel in simpler organisms like mice. And actually, as far as we can tell, and my opinion is, most of the dynamics and the rearrangements of connections happens as you're growing up. Happens as you're a child. For humans, happens as a teenager. For us, really, it happens even into our 20s, sometimes into our 30s. But once you've reached adulthood, what we call adulthood, somebody as old as this guy, it turns out that our synapses don't change very much. They're plastic, but the fundamental architecture that you built as a child with the experiences, your education, et cetera, that kind of stays as your, what we call the wiring diagram, the map of connections for the rest of your life. Now, I'll push back on myself. And there is a field, an idea that synapses are plastic. They have something called plasticity to them, that as adults, we continue to learn. Fair enough. I think that's true. But I think the reason we have, at least in the US, sayings like, you can't teach an old dog new tricks, is actually kind of based on reality. The older you get, the harder it is to change your mind about things. And I think all of us know this. Imagine how many times we changed our mind when we were 12 and 14 and 16 and 18 and et cetera. And how many times you see people in their 60s, 70s, and 80s that change their mind. I think there's a real behavioral difference there. And I think it reflects the fact that over time, our connections become solidified.
Could you explain the difference? Because you have like neuroplasticity, like there's the whole work from Wendy Suzuki about neuroplasticity and movement. But how does that go together with what you're saying, that brains are actually not changing, or the connectome is not changing?
Yeah, I think that probably, and again, I'm speaking without too many clues, but that's okay. I think it's possible, for example, to change not change the wiring diagram, not who you connect with, but how strong you perhaps connect with your existing connections. Whereas childhood perhaps is a much more dramatic change. There you're actually perhaps talking about who your actual partners are. You get to switch from this neuron to this neuron to this neuron, and then back and forth. And that is a kind of deep plasticity or a profound plasticity. Whereas in adults, probably, of course, you can change a little bit of that existing wiring diagram, how loud each or how strong each neuron communicates with each other. But you're never going to have, for example, a neuron in your visual part of your brain talking to some neuron in your auditory part of your brain. But we do know that children, these potential connections exist, because if you damage one part of that brain in a child, it finds other pathways and restores its particular behavior. One of my favorite stories about this, if you don't mind me saying, it's on the internet. It's one of my favorite things on the internet. There's a man who decides to see if he can learn how to ride a reverse bicycle. And what I mean by a reverse bicycle is just that, normally when you turn the handlebars this way, the bike goes this way. But you can imagine building a bike so that when you turn the handlebar this way, the bike goes this way. And he says, that's a pretty simple thing for my brain to understand. How long would it really take me to relearn how to ride this bicycle? And he just documents it. And I can't remember, but it takes him months and months and months and months to learn how to ride a bicycle. And then amazingly, he asks his, I think, 12 or 14-year-old son to figure out how to do it. And it takes his son days to weeks to relearn that. And if you take that kind of data with data about how easy it is for children to learn new languages and how hard it is for adults to learn new languages, I think it seems obvious to me that, of course, adults have plasticity in their brain and learning, but the magic is really what happens when we're children. And my last thing, which is slightly snarky, but keep it out as you want, is that I'm not sure, given that most of the people producing these studies about adult plasticity are adults, I'm not sure there's a little bit of wishful thinking here, that we really want to think that as adults, we're capable of learning like we did as children. But I think reality is the opposite of that.
But I think that's a problem inherent to science, that science is performed by people. So we all have our biases.
That's right.
But there is also, if I'm not mistaken, at least, there are also documentations that some parts of the brain can actually still grow or create new cells even in adulthood. Is it then wrong, or is that something different?
I would say it's controversial. Sorry, let me just be specific. The other thing about neurons, which is different than any other cell in your body, is neurons are something called post-mitotic, which is that another way to say this is that every cell in your body, not your brain, continues to divide and be replaced. So, and I keep wanting to look this up, but let's just make up a number. Every 15 or 20 years, you have an entirely new body. All the cells in that when you're 40 in your body were completely different than the cells that were because they've all been remade. The only set of cells really that do not do that are brains, neurons. So allegedly, you die with the neurons that you're born with, and some regions of the brain in some investigations still show this ability to make new neurons, et cetera. And parts of the brain called the hippocampus and parts of the brain that detect odors or so. But I would say that it's still a little controversial, and it's certainly controversial whether it happens in humans, and certainly whether it happens in adult humans, the sort of behaviors we're talking about. But I'm open to it, and I hope they're right, meaning I, like the other scientists, also want to believe that there's plasticity in my brain and that I'm capable of learning and et cetera. But I don't think it's a foregone conclusion yet.
Now, let's assume we have our connectome in our brain. Is there something like a good or a bad connectome, or is it just different?
Fascinating question. So first, we should ask how hard it would be, but we could save that for a second to get a connectome. So I'm specifically interested in an idea. And again, I'm going to have to tell a story. I'm sorry that I always have to.
We love stories.
Okay, good. And the story starts with maybe why I wanted to be a neuroscientist. Because I didn't originally. I'm Indian. I had Indian parents, like so many other. I was thought, medical school is the right version of this. And when I was in medical school, it was a little bit later after I'd done my PhD. I'd already had my daughter at the time. And when my daughter was young, she had a imaginary friend. And my mom told me that I had an imaginary friend as well. And I was fascinated by this idea. And I happened to be doing a psychiatry rotation at the same time. So I was not only exposed to my daughter, who had imaginary friends, but I was exposed to a lot of adults that had imaginary friends as well, schizophrenics, paranoid schizophrenics, etc. I was super curious whether the mechanism was the same. What's the difference between my daughter's imaginary friend and the imaginary friend of someone we've labeled as a schizophrenic? And at the time, there was a standard sort of interview that you used for adults. And I instead tried the interview as best as I could with my daughter, and then I presented it in medical school. And I think I failed this part of the course, but it was worth it. And I presented it in medical school, but I didn't say the age of the patient. I just said the symptoms and their reactions to my questions. And I realized maybe at that moment that what if many of these disorders, like schizophrenia, et cetera, are just sort of Peter Pan syndromes, meaning they're just brains that refuse to grow up. And we have a set of, as I was saying, we have different sets of connections when we're children versus when we're adults. And so is it possible that some adult illnesses like schizophrenia are just failures of the normal development, meaning imaginary friends are fine in children, but they're problematic in adults. Right? Another story I like to tell is that my wife, when she was young, and this dates her, so I apologize, Elizabeth, she was obsessed with Titanic, the movie. And she's old enough that she had the movie on something called a VHS tape. People in the world know what this is. And she
at least I still do. So
okay, good. And she used to, and this is a thing from that technology, she played that tape so many times that it broke because she had to watch it so many times. Now, if I told you that was my wife currently, you'd say, maybe obsessive compulsive disorder. Maybe there's something there to think about. But of course, in children, these behaviors are considered relatively normal. There's nothing wrong with your daughter or your son insisting that you read them the same bedtime story in the same way again and again and again and again. So there's these ideas that, and I'm getting to your question, so I apologize. So yes, there could be bad wiring diagrams or good wiring connectomes or good connectomes. But another way to think of it is what bad and good means is that wiring diagram appropriate for your stage in life? Because perhaps it's a great connectome to have as a child that fosters creativity, that fosters imagination, that fosters play, etc. But that same wiring diagram, if it refuses to grow up, may cause pathologies in an adult.
That's a super interesting idea. But I think it's also part, before, like many years ago, we would say someone who is mildly autistic, which is just very precise. Now he's autistic. Right. It's also how we define certain things, I think, and that we put people in boxes, but maybe we shouldn't put people in boxes all the time.
Of course, because the skill sets that become successful, the skills that humans have over time change. Thank God success doesn't depend on me hunting animals and providing food. I just don't have that skill set. And the idea that, like, I don't know, when we were hunting hundreds of years ago, I would have been labeled a particular, put in a particular box, but that same skill set, I think, my skill set is more useful now than it was for hunting for exactly this reason. So it's not only the abilities that our wiring diagrams give us, but it's also what society needs at those particular moments. So I see it as a very flexible world without these kinds of labels.
Maybe this is a bit far-fetched, but you think that some of the variety in the connectome is also part of like evolution, in the sense that if you have some random parts and a situation changes, that might be beneficial?
In fact, let me push this. Why is it that humans, with our connectome, we dominate every environment on the planet? You can find humans in the coldest regions in the world. You can find humans in the hottest regions in the world. How did one evolutionary brain deal with all of that? It's because we have brains that are, when we're children, can adopt many different possible configurations. There is all of these random connections that are irrelevant in the Sahara, but incredibly relevant in Antarctica. I'm just making these up. And I think what is incredibly probably now we've looped back to maybe to the very beginning. What is it that is so special about a human brain? My suspicion is that human brains are born with every neuron connected to every possible combination of neuron. And that is the fundamental difference between a human brain and a mouse brain. And that huge combinatorial space of which way a brain could go, depending on its environment, depending on the language it hears, depending on the technology it's exposed to, I think is what makes human brain special.
That's a lot of connections. Do you have some idea of an order of magnitude? How many connections are those?
Yeah, it's a great question. So this gets back, and I'm going to answer like, how crazy is this idea? I think is what you're maybe implicitly asking me.
I'm being polite about it.
I appreciate it. I appreciate it. But so in your brain and everyone's brain listening, we think there's something like 100 billion neurons. And on average, we think of every neuron makes 5 to 10,000 connections and receives, 5 to 10,000 connections. So if you take a number like 10,000 and multiply it by a number like 100 billion, you get some number that is a quadrillion or on order. And that number I don't know what that number means. It's hard for me to think about that number, et cetera. So one way to think about it is that it's maybe 10 times more stars than there are in the Milky Way galaxy. So another way to say this is that human brains contain 10 galaxies worth of connections. And that's what we're trying to map.
That's really insane.
So the answer is it's crazy.
Yeah.
And actually,
in a nutshell, it's all crazy.
Yeah, in fact, just to tell you how crazy it is, and we're starting, is that a mouse brain, which is 1/1000th the volume of a human brain, is probably the next thing we're going to map. And one thing I wanted to add is that the only way you could fit a quadrillion of anything into like a volume like this is to make each of those connections so extremely small that most standard microscopes cannot image them. So we've been working with this older technology that we've been updating. When I say we, I mean people all over the world are doing this, called electron microscopes. And these give you resolution very close to an individual atom on order. So now the real problem shows up. If I'm going to take a volume like this and image it at the resolution close to an atom, I'm going to produce data that nobody has any idea what to do with. So let me just go back to a mouse brain, which is not even 1.1, like around 0.1% of the goal. A mouse brain in the size of data. So let me just make sure I do the analogy well. People probably know at this point what a gigabyte of data is. The stuff we have on our phones. One way to think about it is a gigabyte or so is about what a Hollywood movie takes up on your computer. It might take up less now, but that's how I used to, anyway, think about it. A mouse brain is not a 1,000 gigabytes, which is something called a terabyte. It's not 1,000,000 gigabytes, which is something called a petabyte. It's actually 1 billion gigabytes of data. And just to give you an idea of how ridiculous that is, I'm making myself laugh, sorry. How ridiculous that is if you took all the information, and this is a very American-centric view, so I apologize, but let's say we took all the information in what's called the Library of Congress here, which to some first approximation is the sum total of all human knowledge. And if you took everything in there, every movie, every recording, every written document that a human has ever made in the history of humanity, and you put it all together and you said, how much data is that? And you compared it to the mouse brain is orders of magnitude more data than humans have collected about anything in the history of humanity.
What? What? So pure in terms of the amount of information, there's like immensely more information in the brain of a mouse than the information that's being produced by all humans, or is that something different?
That is a good question. So let me try. That's an excellent question. I really like it because I have another number. That number that I said, which is 1 billion gigabytes or so, it's on order the amount of information that goes up and down the internet every year. And that's including all the, and I'm sorry, I'm going to age myself, the Snapchat pictures and the Instagram videos. If you took up everything that went up into the internet and down into the internet, you get comparable data sizes. So it's not something we don't know how to do, meaning we do it in a distributed fashion already. But you're right. It's mouse brain is about what humans produce in a year.
Actually, because we have been talking about the information in the brain of a mouse, that brings me to one of your papers. I'm gonna pull it up, right? So the title is Isochronic Development of Cortical Synapses in Primates and Mice.
Yes.
So here we're actually comparing part of the brain between primates and mice. Could you tell me a bit more about that?
Yeah, so this is based on just something that we were talking about. What is it that makes a human brain so fundamentally different? And the argument is that human brains take forever to develop. By that, I mean, not only are human brains born hapless, meaning, and I love saying this, when my kids are born, they were useless. Babies
to be fair, I think it's all kids, but okay.
Yeah, fair enough, but I like to make it about including me, as they always point out. As they always point out. Meaning they don't know how to walk, they don't know how to communicate, and they are entirely dependent on us. And very few animals are born that way. Most animals are born knowing how to behave. A horse, soon after it's born, knows how to walk and trot and gallop and all of the things that horses can do. Humans are born in this weird condition where we can't do anything. Even weirder, it takes us decades to grow up. We stay with our parents in the United States almost 20 years. And then we're not done. We got to go to college. And then some of us, including you, we go to graduate school. And then after that, we do we're still training. We're still getting ready. And weirdly, you can be a 40-plus-year-old professor, and you're still asking your parents to help you on that down payment for your new house. So there's something fundamentally slow about us. And the question we asked in that paper is that like a unique thing to humans, or is it graded? Meaning humans take hundreds of years I'm joking, but decades to develop. A primate only takes 10 years to develop, a non-human primate, and a mouse only has 1 year to develop because a mouse can only live for 2 years. So we asked the question, let's take two mammalian species at the very extreme of what we study. And here we're talking about a very specific characteristic, which is lifespan. So a primate, a non-human primate, can live for 20, 30 years. Mouse maybe lives for 2 years. And you may ask, and I think the field thought this, you might expect animals that have shorter lifespans to finish development earlier, to finish their development of the brain earlier than an animal that has a longer lifespan. That sort of makes sense. But crazily, and this is what I love about neuroscience, since we know so little, we actually mapped how the synapses develop in a mouse and a primate. And if you don't look in normalized time, if you don't try to normalize to the lifespan and you just look in absolute time, they develop at the same rate, even though the primate lives for 20 years. And our view is even as the mouse is dying, it's a year and a half old, it's 2 years old, the brain is still developing. And it's still developing at the same rate as a primate does.
What does that mean for us? Because that means that we're declining at some point, but other animals are not.
Exactly. So this implies to us that what makes human brain special, this really slow, protracted development, we think is a quantal event. It's something that just emerges in humans. And perhaps there's some evidence that chimpanzees also have much slower development than other species. Hominids, that's the category that includes us and chimpanzees, et cetera. And so we are making the argument, but we're going to try to get more clues, that this protracted development is really a evolutionary invention of humans and hominids, perhaps more broadly. And it explains why there are no other species as 90% as smart as we are.
I already touched upon it. So how do you research the connectome? You used electron microscopy. I think I've seen in your papers you also use X-rays.
Yes, yes. So we're always looking for new ways to image the brain at nanometer scale resolution, the resolution that you need to map all of these connections in a brain. Most of that work is done with electron microscopy. This technique that I was saying that uses electrons instead of photons to get exquisite resolution in its images. But I actually have a second appointment. I'm also a scientist at a place called Argonne National Laboratory. And Argonne is one of these national labs. Perhaps people have heard of Los Alamos. These are the sort of premier scientific locations in the United States. And they have toys like you would not believe. And the two toys that I love that they have is, first, they have some of the largest computers in the world. And I guess we've already talked about why that would probably be necessary to map a mouse brain. The other thing they have are these things called synchrotron X-ray sources. And they're very similar to the kinds of X-rays that you get when you go to the hospital when you break a leg or whatever. In fact, they're very similar to something called a CT scan, which people are familiar perhaps with, where you go into a machine in a tube and it rotates and it takes X-rays through you and can make a three-dimensional model of you. That's exactly the same idea, except now at Argonne, they're continuing to improve the resolution of X-rays so that they're close to now nanometer resolution. And so one option we would love to do is, instead of for EM, we're forced to slice the brain into thousands and thousands of little image sections and take a picture of each of them. But with an X-ray, one possibility is you just put the whole brain in, you spin it all the way around, and you get the full nanometer wiring diagram of the brain. We haven't proved it yet. And you might say, listen, you don't need more ways to collect the data. You just need more ways to analyze. But we can't help ourselves. We're still looking for new ways to image the brain.
Yeah, but I think also with the slices, one of the problems is the limitation of the thickness of the slices, because at some point you can't make them thinner.
Absolutely. But even here, not us, but neuroscientists all over the world refuse to give up. So there are these now techniques where you can make a slice, take an image of it, and then you can just use something called ion milling to just vaporize the top of that slice, and then take another picture, and then vaporize it, and then take another picture and vaporize it. So you're right. There is a physical limit to the cutting, but even there, we're trying to overcome those physical limits with other technologies. I'm constantly, again, another analogy. I sometimes worry that when I tell you that I'm going to map a human brain, it's a lot like if we were in the early 20th, late 19th century, and you own a balloon and I own a Zeppelin, helium, whatever. And the two of us are arguing about which one is going to get to the moon first.
Okay.
And you say, well, my balloon is 10 feet higher than yours. And I say, well, my Zeppelin can go 3 times faster. We both know none of those things are making it to the moon. And so there's always, I'm always worried that even the existing technology that we have is more like blimps and Zeppelins and balloons and et cetera. So I'm constantly looking for the potential rocket ship.
A great analogy. And sometimes our questions are bigger than our current systems that we have to answer them.
I would say not even sometimes, most of the times. And not only that, we are entirely confident sometimes that our techniques can answer those questions. And I think that's another kind of bias that gets you into trouble.
I'm actually now reading the three-body problem. I don't know if you read it.
Oh,
I think it comes very close to what you're saying right now, no?
Oh, I would love it. It's one of my favorite books. How so?
In the books, there were these limitations that were put on technology.
Yes.
Yeah, and they were also trying to evolve. But at some point, they reached the limitations and they weren't able to answer the question that they had because they had those limitations. And once those limitations were lifted, only then could they proceed. And it feels like it's more or less what you're saying right now, but in real life.
Yeah, in fact, if I could just add Another crazy statement. I not only believe, I believe this with every part of me, meaning, let me say it a different way. Ideas about the brain or biology are not the important part. We like to think ideas and hypotheses are important because they come from us and we're biased. But I think if you really look at the history of science and how progress is made, it is almost always technology that drives scientific progress. It's almost never hypotheses and ideas that drive it forward. It's almost always technology.
To push back on that a little bit,
Please.
technology is also based on ideas. How is it developed? So
excellent point. Excellent point. The only thing I like, excellent point, is that when you have ideas about technology, they're usually measurable. You know you're making progress because you say, I want this thing to go this fast. And you have a way to measure it. And you say, okay, now it is this fast. I want it to go this fast. I find it hard to map quantitatively the progress in biological ideas in the same sense. And I'll say one more thing. The real hard problem for me with ideas and hypotheses is that most scientists fall in love with them. And if you think about it, if you're a famous, I'm not, sorry, but if you were a famous scientist, and you
I think you are a bit, at least. Come on.
We'll leave
Okay.
it. Maybe now. But and you're famous because you have a hypothesis or an idea about how something works. What is your vested interest in hearing about data that is contrary to that hypothesis? Of course, as a scientist, you have to. But as a human being with biases and unconscious sometimes, you probably don't want to know about that. And so I worry that ideas about biology, which are often hard to prove and it's hard to figure out progress, those are much more susceptible to this kind of bias than having very few ideas and just trying a new technology on a brain.
Yeah, no, I think that's completely true. And also, not even if it's a personal hypothesis, but if it's a hypothesis that has been established for years, and then it's really hard to even suggest that something else might be the correct answer.
In fact, there are two things. There are two sayings. There's a saying that I love. It's a saying by Max Planck, who's a very famous Nobel-winning physicist, and I believe he says, "Science advances with every funeral." And the idea is that these ideas, which get into people's heads, and they're eminent and famous, you really can't move past that idea until that person is gone. There's no sort of rational way to accomplish this. And in fact, if your audience would, one of my favorite books about how science is done is a book by Thomas Kuhn, and it's called The Structure of Scientific Revolutions. And Kuhn is the one who invents or develops the word called paradigm shifts, which is now a common word, but I think originally comes from Kuhn's Structure of Scientific Revolutions. And he says the way science advances is at any one moment, all the scientists in a particular field at a particular moment in time, they're there to preserve how they think that process works because that they developed it. And usually the way science works, he says, is that you have somebody discovers some unexpected fact, whether it's black body radiation for Einstein, or it's how the traveling of the planets by Galileo. These facts then become like the piece of dirt that gets inside an oyster. They irritate the scientific field, until they cause the entire worldview to collapse at one moment and replace it with an entirely new worldview. Quantum mechanics replaces classical mechanics. In the modern world, it used to be that we thought all the planets revolved around the Earth, the geocentric view. Galileo shows that there's data from his telescopes that says this is impossible, and the planets have to revolve around the sun. And it's not a gradual thing. It's a remarkably quick thing. And so my philosophy as a scientist is I'm not interested in trying to prove or disprove hypotheses. I am interested in finding that surprise that will overturn the existing worldview and replace it with a paradigm shift.
I hope you can find it. That will be, yeah.
Right. And in fact, a separate way to say this is a terrible thing to say is that one reason to do the connectome is not because I have any particular reason why, right? But because if you collect such a new novel data set about a brain that's never been collected before, there have to be surprises in that data set. Now, I can't get grants saying this.
Yeah.
I wouldn't have gotten tenure saying this, but I think that's the reality of it.
Yeah, that's actually a very good point. But to go back to that, because you said that's a massive amount of data, and it's very difficult to work with that. So how do you even do that? How do you manage those data?
Yeah, so there is no way even for a small fraction of a mouse brain. So let me say it a different way. That mouse brain that I said would be billions of gigabytes of data. If you had every human being who's living on Earth, and in fact, I think if you had every human being who's ever lived on Earth working a 40-hour week, tracing neurons and identifying connections in that mouse brain data set, they won't finish. They'll take them 1,000 years or something to finish. So the entire endeavor rests on AI, artificial intelligence algorithms, analyzing those data sets as accurately as human beings can analyze those data sets. Now, that's good news, bad news. I mean, bad news is, holy, we need some pretty good algorithms to do it. The good news, we claim, is that AI for looking at things and determining what they are is a pretty sophisticated field with billions of dollars of investment in it. It's what Waymo needs to solve for automatic driving. It's what the other car company, Tesla needs to solve, for many of the things. There's a huge endeavor, and AI continues to accelerate in ways that we give us confidence, not certainty, but confidence that we will be able to apply it. And in fact, it's interesting. One of my close friends, a close collaborator, a leader in this field of connectomics, a guy named Jeroen Jain, works at Google. And Google has one of the best and largest efforts to reconstructing connectomes. Google and my former postdoc mentor, Jeff Lichtman, just published the largest connectome of a small fraction of a human brain. So we think there's help from industry. We think there's help from, but we're going to need all that help.
Based on what you know now from AI, is the difference between multiple brains very big in terms of connectome?
This, again, you're asking great questions. And let me tell you how depressing this is. We had this idea for a long time that every human or mammalian connectome would be the same, that there should, would be different, excuse me. There'd be huge variability among humans or so. But there was also this idea that in perhaps smaller organisms like flies or worms, they should have the identical connectome, because to some first approximation, what is individual variability in a fly? It exists, but it's not so much that we should. So because we're starting the mouse, other groups have already done small parts of the fly brain. And for the first time, they've done more than one fly brain. Literally, we're up to 2 halves, I think, which is how far the field has. And we're already seeing huge variability in fly brains, not even at the level of connections, but the level of the numbers of neurons. So a brain region in a fly brain, in one fly might have 10 neurons, and another one might have 20. And so one of the things we're going to have to deal with is, what is the variability from connectome to connectome to connectome? And I think it's a fair argument to say, if the connectomes are highly variable, but the animals are all kind of the same, maybe the connectome doesn't matter as much as you think it does.
That would be a shame, though.
Well, I don't know. Of course it would be a shame. Wait, let me say, please, of course it would be a shame. But, there is a view that another way we progress is by excluding possibilities. And it sucks broadly, but it's real progress at some level. Knowing that the wiring diagram is not the main driver of some of these things. Of course, I have to say this because I need some way to, when I fail,
No,
to
but I think that
justify the millions of dollars people have given me. But I think this is the best justification I have.
no, but I think that's a very fair point, because I have met actually a few PhD students, and it's normal. Often things don't work out when you're doing experiments, but PhD students often go bonkers. It's like, I have nothing, I have no PhD, but negative results are also results, and it's not fun, but it does help us forward.
Yeah, in fact, again, because I really like this idea of the philosophy of science. I feel like all science is philosophy, and all it really is just choosing how you do science. That is the most important choice, not what you study or what tech. It's your worldview, how you think about it. I think is the most important thing. So the other incredibly famous philosopher of science, not Thomas Kuhn, is a guy named Popper, Popper. And he actually came up with, I think, the only formal way to do science. He says, look, we don't do deductive science. We don't start with a proof and then, an axiom and make a proof like we would do geometry. We are inductive scientists, not deductive scientists. And he gives this analogy. He says, how would you prove that there is no such thing as a black swan in the world? And the only way you could do it is every day you go out and you count swans and you say, I saw 10 swans and they were all white today. So the probability of a black swan goes down. Then I go out the next day, another 10. So you could always reduce the probability that there is a black swan, but you can never prove that there is no black swan. And in fact, what we should be doing is falsifying our hypotheses. It's the only way forward. If you find data consistent with your hypothesis, you haven't actually done science. What you've done, and again, I really tried hard to annoy everybody. So let's see how it goes. That, I think, is more what we call conspiracy theories, because what you're looking for is facts that conspire to prove your hypotheses right. And I think that is what is broadly wrong with conspiracy theories. And I think that's broadly wrong, what's wrong with a lot of modern science. We have lost the idea that what we should be doing is disproving our hypotheses. And now you're right. Students, my students, your students, everybody's students says, holy crap, I got a whole bunch of negative results. And then you think, no, that's science. That's the science part.
Yeah. If we're going into philosophy a bit, if you put the whole connectome of a person
Yes.
in a computer, would it be that person?
I love this question. And I think it's profoundly important. As confident as I was to you in the first part of this discussion, where I said, look, those synapses contain everything about you. They contain every thought, and et cetera. I almost have to say, yes, if you put that into a computer and you simulated it, some part of you would be alive in that computer. Now, would it be all of you? I don't know. There are things in our body. There's soup, if you will. There are things that are not found in the wiring diagram. Maybe those are the things that make you happy or sad or angry. So yes, you could be inside the computer and know all the facts that you know and have all your memories. But you could be really upset because those kinds of things are not in the wiring diagram. But to be fair, that I think is the right test of this, not with a human yet, but people are already, for example, maybe this is worth saying, the only wiring connectome that has ever been done has been done of a very small worm that has 302 neurons called C. elegans. And they did the whole thing by hand, and they did it in the 80s. And it's the only time it's been mapped. There are people now who have taken that wire, now that the computing has gotten sophisticated enough. There are now people who are taking that wiring diagram, making a fake worm with fake muscles and inside a computer, and asking, how well can I simulate the behavior of that worm from the wiring diagram and these other lessons alone?
And what are some of the results?
I think they're just starting, actually. So probably in 6 months or a year, they'll have something. And I think, to me, it's not an obvious question which way it can go, or it's not even clear that it's going to be a black or white answer. But I find it fascinating. But I would ask, because this is often I think about this. Is it you? Is an interesting question. And let me ask. Let's say I had a similar analogous experiment. I could clone you instantly. And now, right now, there's a clone sitting right next to you. And I do that, I don't know, there's some movie, and I give you each guns. Sorry, it's a US thing.
Sorry.
A terrible analogy. It always it comes to me, but it's because I'm by it. And,
That's okay. That's okay.
and I say, listen, only one of you is allowed to leave this room. You're identical clones to each other. Would you feel okay saying like, okay, I'll just kill you could go on and go. I'll just shoot. I'm good, right? I don't think so. I think even if that person was identical to you, there's some feeling that I'm still here, even though that person, and I'm not gonna sacrifice for that person, even though it's identical to me. And I think these are the kinds of thought experiments where I'm super interested in this idea of uploading people and immortality and living forever. But I do think it's going to be interesting. It's not obvious to me that I would feel about an upload the way I feel about myself.
No, yeah, I mean, we have a fundamental drive to survive, even though there's some copy there. We still want to survive ourselves as well.
Yes. I don't think identical twins are, which is the closest approximation of that we're talking about. I don't think identical twins have this feeling of, it's okay, I'm gone. There's another one right there.
Yeah.
So I think you're right.
And if we don't give anyone a gun, if we don't kill anyone, but we put the connectome in the computer, there's still the question of, like, you have all the right connections,
Yes,
but maybe the voltages are different, for example. So
absolutely.
And that can have different results as well.
Absolutely. Absolutely. Now, the people who argue would say, doesn't matter. I could simulate 1 billion universes. And in one of those universes, the voltages will be right, et cetera. I don't know enough about simulation. I don't know enough about what a huge parameter space this is. And so I'm agnostic about this. And also, the last thing I'd say, and this is really going to annoy people, it's not obvious to me that if I uploaded myself into a computer, some future generation is going to care about what I think about. It's a kind of narcissism on our part to imagine that we have to live forever, that we need to extend. Why? What is so special about me that, 100 years in the future, they're going to care about my worldview? Let me put it another way. If we just resurrected somebody from 300 years ago, I think it'd be fun and be interesting and, but are they going to offer me deep insights into life today that I'm not sure.
Yeah, I think that's a big part of that is vanity. I think
It is
vanity and maybe also fear of dying.
fear. Absolutely. Absolutely. Right. I mean, perfectly normal, reasonable, I don't know, reasonable, but normal human reactions. And so these are interesting conversations, but I often think, why? What do we care? Right. I'm here. I try to live my life as to the fullest and funnest. And we have children. We have ways to propagate our ideas into the future. Books, papers, children. It happens. What do I need to be there? What does my consciousness need to be there for?
Yeah, sometimes I love to read, so I'm definitely going to read the books you recommended. But that sometimes it feels like time traveling or something, or even traveling into someone's brain, and that's
it is. It's fascinating.
It's so interesting.
It's fascinating, especially, of course, nonfiction, but there's fiction that makes me think, how did this person hack into my brain? Meaning, like, I'll read something in a book, and it's still rattling around in my neurons and my connections.
Yeah.
20 years later. And you think, how did this person, I don't know, let's say Shakespeare from 500 years ago, he came up with a set of words that when my eyes read them and produced electrical activity in my brain, it changed my life. Like, how does that happen?
That is so insane. And it happens so often. And I think that's something that a lot of people forget. Like I try to read both science and also fiction,
Yes.
but people always think fiction is just you're just relaxing, and it is relaxing for me. But you also still learn things, like you say, it can change things in your brain
Yes.
that are staying there for the next decade.
Yes. And it's not, and it's happening, you hear music, you see a movie,
Mm.
every one of these artistic expression, sculpture. I'm often amazed how these people have these hacks. Like, let me say it a different way. They may know more about how brains work than all the neuroscientists in the world. Not in the quantitative sense, but they know something about how brains make memories. Because otherwise, how could they have produced this piece of art that hacked our memory system and is now a part of it?
And also, it's something, there's a lot of even trivial things about art. For example, how do you know when it's finished?
Yes.
I mean, yeah, you can keep working on it forever, but you can also say
Amazing.
it's finished. That's it. How do you know?
By the way, it's the same for science or a scientific paper. We choose we say, okay, four figures means it's a science paper. What?
Yeah. No, that's a very good point. Now, we have been talking a lot about the connectome. What have we learned and could we learn in the future from the connectome?
Yeah. And so one of the things we've learned is that we think that a lot of these connections in brains are not random or not even probabilistic, that there are specific rules that try to choose some set of connections and other set of connections. Those may be molecular cues, meaning some neuron here expresses some molecule and this one expresses the equivalent and they lock together. It could be testing over lifetimes, but we're starting to get this idea that the pattern of connections is fundamentally specific and there exists for a reason, not happenstance, which was an idea. And I think that's an important lesson. And then moving forward, I'm biased. For me, the most important thing we can learn from the connectome is how human brains grow up, because I think it is the only, I'm biased again, it's the only question in neuroscience that's profoundly important. What is it about these things that have allowed us to create all of this? That's what I hope to learn.
Do you think it will also help us is maybe the wrong word, but help us understand art or make, I mean, because sometimes like you said, it feels like some people know the hacks of art, how to make a great piece of art. So that's something in the brain, no?
Profound. It has to be. I would love it. I mean, I have often thought I should have a side project on my lab where I'm just talking to artists and writers and et cetera, and just ask them if you had the wiring diagram of a human brain, or even what is it that you want to know about the physical basis of a brain that would help you maybe a better artist? And maybe that instead of me trying to figure out what that would be, I should just go ask the experts. And over time and having them think about it might be the best possible answer for what I should look for.
Well, if you ever get the funding, you should really do it.
Yeah. It's the funding. Again, it's almost as crazy to say I don't have hypotheses and I just want to make. I'm trying to imagine how the National Institutes of Health, the major. I say I want to collect all these artists and I want to just spend time. It just sounds like I'm scamming them because I just like hanging out with artists and talking to them.
Well, we're running out of time, but before we close, do you have a take-home message for our listeners?
I don't have a take-home message, but I wanted to say to you, I think we're at a time now where the public view of science is starting to worry me. And it's not exactly obvious to me how we went from sort of holding science as one of these incredibly valuable things that society does to where it is now, where we don't trust anything or know anything. And I think this kind of communication and outreach is the best chance we have. So I really appreciate, first, of course, I appreciate you asking me. Thank you. But I also more broadly, really, I think this might be in fact, is more important than most of the science that is actually happening. I think this idea that we need to get people maybe the right way isn't to get to trust science, but to at least understand scientists and know what their motivations are and how they're people just like us and they're trying as hard as they can, et cetera. I think I'd like to make the case is the most important thing that we have to do currently. So I really appreciate that you're doing it.
It really means a lot to me. I appreciate it so much. And thank you for being here as well, because you're such an expert in the field, and I love talking to you and work or learning from you, actually. So thank you so much.
Yes, and I hope we get to talk again soon.
Yeah, I would love that. I would love that. This was Apple Finch Pudding. I want to thank Bobby Kasthuri for the information. Let's meet again for the next episode of Apple Finch Pudding.